All right, so we have 15 minutes left for questions.
So I have a question regarding slide 69, where you described in the last line that the higher trend slope gives lower quit probability. By higher, you said even though it was negative. Do you mean the absolute value, or do you mean just higher regardless of sign? So just approaching.
So if the average is like this, I'm thinking that when it increases like this, that is getting towards flat. That is, the urge level doesn't go down quickly enough. The person has a low probability of quitting. They have too strong of an urge. It's a little tricky when you talk about negative slopes and effects, but it means that this person is higher than average. So therefore, closer to a flat line of urge. Urge doesn't go down. Quit probability is low.
Okay. And then I have a second question about, sorry. Oh, on slide 74.
Slide 74.
When you talk about the effect of the negative affect on smoking urge is reduced over time, could this be related to there being more variance around negative affect to begin with, and therefore it's kind of a diluted contributor?
Could you say the last part of your question again?
Could this be related to there being more variance around negative affect in general, such that it's kind of a diluted contributor over time? Because I noticed that back on slide...
Oh, because we saw that in the Bergman data, you mean?
Right.
In the last data set. Yeah.
Right.
It's not the same data set, so I don't know. The negative affect distribution is actually quite different in the two data sets. It's very skewed in the Bergman data that we did the factor analysis on, but for the smoking sample, it's quite normal. Okay. These smokers are high-wired. I mean, they're irritable.
And then you keep asking them if they have the urge to smoke.
I'm sorry, what?
And then you keep asking them over and over if they have the urge to smoke.
Right. I mean, it's really irritating. So I don't know, but that's an interesting angle. Does it have to do, the lower slope doesn't have to do with change in variance over time? That's a good point.
I have a question.
Yes.
So I work with a lot of biomechanists who tend to conduct studies on a small number of people, but they'll measure things in time series. So they'll measure EMG forces on a AMG on a muscle while somebody's doing a task, or they'll measure forces on a joint while they're doing a task. And what they tend to do with the data is collapse it in much the same way that you showed the animation for the Bayesian time series onto a distribution, and then pull out a particular parameter from the distribution to analyze. And I'm wondering if you've seen any biomechanists trying to use some of these techniques to look at these data more dynamically.
By the way, you reminded me that I didn't give proper credit for that movie that's Morten Schultzberg's doing.
Yeah.
So do we have any biomechanical person in the audience?
I'm just really excited about this because I can see lots of applications for these data that they're collecting to look at it in a different way, and we might see different things.
Right. So part of your question is how can we do good analysis with few people but many, many time points? I think that again falls in the lap of part 7 tomorrow afternoon.
Okay.
And it's related to work maybe also by people like Steve Boker and Simin Chow, which they have data. Like,
Do you want to talk into that microphone?
oh, yeah. Getting there. So people like Simin Chow and Steve Boker, they use data like the movement of people's heads during conversations and this kind of stuff. So, and they definitely look at the dynamics. So what you are saying is like when you collapse it, you get a summary of the distribution, but you lose all the information about the dynamics. And they specifically use continuous time models to model the dynamics of those kind of data.
So I might come and ask you about those names later.
Sure.
Okay, thanks.
On slide 68, I just had...
Slide 68?
Yeah, I had a quick question about the code. So for the first line under between with urge... No, keep going down. For the first code of line under between... So for urge, SYX, S, so on, you mentioned that those were random effects. Can you clarify the random effect that is urge in that line of code, please?
Yeah, so when I refer to urge here, that's the random intercept, or actually which turns out to be a random mean.
Okay.
So that's the mu sub I in Ellen's presentation.
Okay, thank you.
Yeah.
On slide 60, with the cross-classified, so the time QD as one of the cluster IDs, is that the bin number essentially that's created with the T interval in terms of identifying the cluster membership for that cross-classified?
Yeah, these two variables are the same, but here, the binning here creates a new time variable that's used in the actual analysis.
But when you're putting I mean, in terms of the cluster ID, right? If everyone's time, if it's a continuous time, then observations will go into the same bin, but the actual, recorded time QD value is going to be different for every single observation, potentially. But you're binning them. So is it the bins that form the cluster ID for time?
Timur, why don't you come up and take that question at the microphone there?
Yeah, that's right.
Why didn't I think of that?
This is already the integers. Yeah.
Could you repeat Catherine's conclusion?
So the question is if this is a cluster variable, so you can't really be the continuous time variable, which is takes all kinds of values.
Right.
So when we are using this, so this is about how the t-interval command works in cross-classified models, and that's how it works. We first make it an integer in whichever, using the algorithm, and it's a slightly different algorithm for cross-classified than it's for two-level because the time scale is aligned. But we first make it into an integer, and then we do use it as the integer as the cluster command, basically.
So are you saying that this time QD variable in the cluster setting is the one that's created by t-interval?
Right. Mm-hmm.
And it's not the original time QD sitting up there?
It's correct, yeah. We can accept, Mplus wouldn't actually take a non-integer cluster variable.
So this variable could be like 1.32 or 0.32 that we saw, and we turn it into, say, 1 by this statement, and that's the value for time QD that's used for the cluster variable. Was that what you asked?
Yeah.
Good. All right. Thank you, Timur.
I had a question about slide 57.
Slide 57. I'm learning a lot here.
So I was wondering if this comparison between autocorrelation with the regular and the residual is something you can do on the current version of Mplus, or is that upcoming?
This is upcoming. Version 8.1 is upcoming. So this line you cannot do in 8.0. You can only do this. You can only do that, not that.
Okay, thank you.
Yep.
Actually, I want to say something about it.
Yeah.
So, we do have, you can do it. The language isn't available. The model is available, with this mirror approximation. So I'll talk about this tomorrow. But, technically you can do it.
Technically you can do it, but it doesn't work as well as it will in 8.1.
So the algorithm that comes in version 8.1 is very efficient. So we were just talking with JP about this, and he had to take 50,000 iterations, I think, to get it to converge for the example that he worked with. But now with the simulation study that we're running in the developmental version, this algorithm converges in 200 iterations. It's like one bam bam and it's done. So it's worth it to actually get this algorithm actually implemented fully and available, because it's so much more efficient than the current implementation, which basically goes through the mirror model.
Yeah.
So
how fast did you say that it converged?
bam bam.
Hi, JP.
Thank you, Bank.
Are you going to ask another question that sends us back 5 years?
Well, thank you for this presentation. I did have a question about this slide and the previous slide, actually. So, I've been thinking about this issue a lot. And the next slide kind of implies that one of the ways that you should decide is based on fit, right? And I'm thinking about this more, now if you go back to the previous slide, yeah, I'm thinking from more a substantive perspective, it even seems that I could envision a situation where you actually can estimate both auto regression.
I see
and
Tiamer approaching the microphone here.
Correlation.
So we actually have like about 10 slides on this tomorrow, and we call this the joint effect model that has that has both. Actually, sorry, I maybe interrupted you.
Oh. No, you probably are figuring it out already, but I'm just
so
thinking
you're saying having both this and this. I think Tiamer is going to talk about effects of negative affect.
No, is that what you were talking about?
Yeah, because substantively, I can envision that even if you take into account earlier urges predicting later urges, that, for example, there could be, like if you have a cold on a particular day, maybe that affects your urge the next day, separate from the urge itself, and so I'm just wondering if you had any thoughts on that. I'm not expecting you to build this in anytime soon. If it's even possible, you probably need more data to be able to even identify this model, more predictors. But substantively, I guess the point is,
you can imagine both.
I can imagine both, even though on the next slide you're suggesting that really kind of you decide based on fit, whereas I'm thinking perhaps the question can guide which one really is the one you should use.
Sure.
Just for me, when I was thinking about this, was basically whether to put the regression on the predictor within the autoregressive equation or outside of the autoregressive equation, and we.
So it has to do with this regression, right? That you were thinking about.
Whether that. And now we know that you can actually have you can have the effect of the covariate in both in the autoregressive equation and outside of the autoregressive equation. So that's what I was gonna show tomorrow, some simulations and explain that model. But that might very well be the case. I have not run any models like that, but
once
seems
again,
quite reasonable
you've
that
given
you'll
us
be,
something to think about.
Yeah, it probably is identified. So.
Every 5 years he comes around and. All right. Yeah. Okay. Great. Thanks.
This might be one of your easier questions of the afternoon. On slide 87, when you talk about 56 times 10 variables, is the limit for Mplus still 500 variables per model? Or is that limit changed?
In a single wide format analysis?
Yeah.
Is the limit 500 variables?
I think they changed it.
I think we changed. I think we increased it.
What is it now, out of curiosity?
I think it's probably 1,000.
Yeah.
I have no idea.
No, but that sounds familiar to me. This is where we have to ask Tui and Wen.
That's what he said in Zurich.
Oh yeah.
1,000.
What did you say?
He said that when we were in Zurich.
Oh, good. You have good memory. All right. Next question. Here we have people. Oh, okay. Go ahead. The person who has the microphone.
I had the mic, so I just thought I'd start.
There you are.
So something that we do a lot, we do daily diary study, and instead of getting the variance for each individual, we'll get the mean squared successive deviation.
Right.
Which some people argue is more so what you want to get at for time series data. Have you guys thought about that within your framework?
I have noticed that measure, and I wondered myself. So it sounds almost like it has to do with amplitude. Ellen has some thoughts on that.
Yeah, actually that's discussed in the paper with Wang as the first author, so Wang, Hamaker, and Bergerman. And we compare the mean successive difference squared successive difference, as you'd say, with the multi-level AR1 model. So, and it's, I mean, I guess you could argue for both, you know, but in the paper, what we argue is that if you look at the mean squared successive difference, this combines both autoregression and individual differences in autoregression and individual differences in variance. So it depends on how you want to look at it. I mean, sometimes I think it's a good idea, but if you think about the mean squared successive difference as a model, like it's the variance of the square of the difference, it's like an AR1 model where you fix the AR parameter to 1. So it's like a random walk. And that's definitely not what most variables behave like. So it's not so much, I would say it's not a model, it's more a descriptive measure. Whereas an AR1 model, it's a model, you can think of it as really like this could be the data generating process, or you could think of it as something that gives you descriptives of the data, an AR parameter and a variance term. So I think it's an interesting thing to look at. There is some description of the comparison in the paper by Wang, but I'm sure other people will have a different take on it than in their paper.
Thank you. And talking about random walks, there's a short walk to the party that has just started and which will end at 6 o'clock. So just know that further questions will impede on the partying. But feel free to ask a few more questions, those who want to. Now.
Okay, may I ask a question?
Yeah.
Okay, so this is going back to the question of...
You have to put your mic very close to your mouth.
Sorry, my apologies.
There you are.
So if we can go back to slide 57.
What do you say?
57.
57.
Thank you. So I recall reading in one of your papers, and I think it's also mentioned today, that these fit indices may not function in the same manner with Bayes as, let's say, BIC and other values.
Right.
So is it possible to test nested models with the Bayes approach? I mean, you're showing two different fit indices here, for example, and I'm wondering if we can really make a determination if one model is a better fit versus the other, if they're not.
You know, that
nested.
topic is going to be covered in detail
Later.
tomorrow morning.
Oh, okay.
So that's in the more technical section.
Thank you very much.
You'll get your fill of the answers there.
I appreciate
But
it.
thanks. All right, over here, final question.
Okay, so can I ask you about whether we can do joint modeling with a discrete time survival analysis with the method that we learned today? Yeah. Okay, thank you.